Students, this is the test review video for the test on area under a curve part 2. And in your packet, it might not be page 30. It depends on what year you're taking this course and how the page numbers have changed. But the test topics, as you can see, are over here on the left-hand side. You will be evaluating definite integrals, which is the fundamental theorem of calculus part 1. So there's the definite integrals. Definite integrals involving, I think that's supposed to say absolute value. So add that in. Pay close attention to that. Make sure that you know the difference and can write integrals for distance versus displacement. The reading that we did on speed, having to look at acceleration and velocity. Don't forget about things we've done in the past, like the trapezoidal rule. Anti-differentiation with an initial condition, so that would be an indefinite integral, but the initial condition was a recent lesson. Average value, remember words matter, and there is an entire write-up and a page in your notes that talk about the words and how to understand what the words want you to do. The mean value is certainly connected with average value. Number 10 is not on the test for 2021. So for students in the year 2021, you will not express a limit as a definite integral, so you can get rid of that. There's the fundamental theorem of calculus part 2, which is taking the derivative of a definite integral. Evaluating definite integrals with initial condition geometrically. That was our recent lesson. There's an area under a curve summary page in your packet. Now, the pages that are listed in the middle of this are not valid anymore for updated packets. However, the textbook problems on the right-hand side are valid. Now, as you use this test review, obviously you will move through test items or particular items that you might need support and or help with, and will probably not watch the whole thing. However, I want to give you some suggestions about how to use the video. Rather than watch me do problems, if you're stuck on a problem and you need to use this video to help you with the problem, watch just enough to allow you to get started on the problem. In other words, listen to what I say, listen to how I break down the problem, stop the video, try to do it, and then compare your answer to mine or to the solutions that are in your packet. All right, so I'm going to go ahead and get started here on this first problem. The directions are show all of your work, and it says no calculator unless otherwise stated. Now, some of these problems are calculator problems. So, for example, in number 1, it says straight up, first problem, calculator permitted. All right, I'm going to read the problem. Listen carefully to how I break down the words. What is the average value of f of x? So that phrase right there tells me that I'm going to use the average value formula on the function of f of x. So I'm going to integrate. Average value is calculus. I'm going from 1 to 5. So I'm going to accumulate the area under f of x, which in this case is cosine of x. And in order to create an average, we have to divide by 1 over b minus a. 1 over 5 minus 1 is 4. Now I'm going to take out my calculator, and I'm going to show you how to do this on the calculator. I think most of you do know how to do that. Whenever I have fractions to type in, I put parentheses around them just to be on the safe side, or in this case, I would probably change this into, 0.25, but I'm going to use fractions just to show you what I would do. 1, if it wasn't a decimal that I could easily convert. So there's my 1/4. I'm going to do math number 9. And it's telling me from and to. If you have an older model calculator, I'll remind you how to do that in just a second. So from 1 to 5 And the function in this case, I did not put it in y number 1 because I'm only using it one time for this particular problem. So there's no need for me to put it. If it was a free response and I was going to use this function multiple times, I probably would put it into y number 1. I'm going to go to my mode and make sure I'm in radian mode. I'm not. I must have been doing something recently in degree mode. So change into radian mode, second quit. All right, and then I'm going to press enter, and I get an answer of negative 0.450. Make sure that you go 3 decimal places. Whoops. Make sure that you go 3 decimal places for calculus. So negative 0.450 is my answer. Now, if you have an older model calculator, the way that you use that, let me get this to be big again. There we go. When you press math number 9 on your calculator, so it would look something like this for you. This is how you would type it on the older model calculator. 1 divided by 4, so there's your division. And then when you press math 9, it's going to say f int with a parenthesis. So the first thing you're going to type in is the function. This is how you always integrate using the older model calculators. You're going to put in the variable of x just to tell the calculator we're working in terms of x, comma, and the comma is directly above the number 7. A lot of people have trouble finding the comma. 1, 5, close, enter, and you'll get exactly the same answer. So you are not at any disadvantage by having an older model calculator. In number 2, if the average value of a function is 10, so in this case they're telling you the average value of f of x is 10. Well, let's interpret that. That literally means 1 over b minus a from a to b of f of x dx is equal to 10. That is what that statement right there tells me. Literally, I converted it out of words and into mathematics. I found the average value, which is calculus, of the function f. And then it says, if you isolate, this is really what it's saying right here, if you isolate the integral and get the integral by itself, which means if we get rid of the 1 over b minus a, what will we get? Well, algebraically, to get rid of the 1 over b minus a, we're going to multiply both sides by b minus a, and that will give me 10 times b minus a, which is, equal to, which is the same thing as 10b minus 10a, and that is letter C. Number 3 is a calculator permitted problem. They're telling us that there is a derivative. Some function has a derivative of ln of 2 plus sine x. If f of 3, there's an initial condition, so we could write it as an ordered pair. That might be helpful. We'll see. What is the value of f of 5? All right, so take a look at what you have here. They're asking us questions about f original. F original. What are they giving me? F prime. So to get back to F original, remember this is a very recent lesson that we just did. We are going to take the amount of area that was accumulated already. So in other words, right here there are 4 units of area. So I start with 4 units of area. I'm going to add that to. Now, where was the x value? Well, the accumulation had gone up to 3. So I had 4 units of area. I'm going to continue accumulating area from 3, and I'm going to stop the area accumulation at 5. I'm going to take f prime, which is right here, ln of 2 plus sine x dx. I'm going to bring my calculator back up and let that do some work for me. I'm going to type literally what I see, so that is 4 plus, and remember we're looking at math, it's number 9, you will get used to that, math number 9, from 3, to 5, And the function in this case is ln of 2 plus sine x. And remember, I did make sure that my calculator was back in radian mode. Let's see, I need a parenthesis around that. And I'm going to get out of there. Parentheses can be one of the most difficult things to make sure that you have a closed parenthesis for every open parenthesis. So don't be in a rush on your calculator. If you have the older model calculators, remember I just showed you how to get that in. And so I get 4.555. Remember, you are absolutely required to use 3 decimal places. 4.555. Let me minimize that and get it out of my way. 4.555 is letter, 4.555 is letter D. Number 4 is a very interesting problem. It has a lot of mathematical symbols in it. It says the limit, oh no, that's what students say, limit as h approaches 0 of 1 over h of the integral of x to x plus h of f of t dt. What the heck? Now, hopefully you were alerted by the limit as h approaches 0 and there's h's in there. I hope you are wondering, is this somehow a derivative? Well, instead of getting overwhelmed by that, let's just go to the innermost part of this problem, and let's just do one thing at a time. So if we were to find the antiderivative of little f, we could say the antiderivative of little f, I'm going to come down here, would be big F of x. And then we would evaluate that. So this would be the FTC part 1. So I'm ignoring the divide by h. I'm ignoring the limit as h approaches 0. I'm just doing the problem bit by bit, starting on the innermost part and working my way out. I'm using the FTC part 1. So I will evaluate big F at the upper bound. So x plus h minus f of x. That takes care of that part right there. Now I'm going to bring back the next part of the problem, which says, hey, take whatever you were doing and divide it by h. Hopefully you're starting to see it. Looks like a derivative is starting to appear before our very eyes. And then go back and get the last part, and then we're supposed to take the limit as h goes to 0 of what we see. So when you look at what you created right here, hopefully you go, oh, that makes a lot of sense. That's the derivative of big F of x at no particular value. There are no numbers in here. So from our work, we know that the derivative of big F of x is little f of x, which is letter D. Problem number 5. Let's read carefully. What is the line linearization, but there's the root word, so I know I'm writing the equation of a line that guides my thinking. What is the linearization of f of x? So to write the equation of a line, I need slope, which is derivative at x equal to pi. So I know the x coordinate is pi. And to get the y coordinate, I have to find f of pi, which means I'm going to substitute pi right here. And so that's nice and easy. If I anti-differentiate or evaluate the definite integral and accumulate area from pi to pi, I get no area. So f of pi is equal to 0. So that's a good thing. The only thing that I have left to figure out is the slope, and slope is derivative at x equal to pi. So I'm going to find f prime of x, which means I'm taking the derivative of a definite integral. So our lower bound is a constant. That's a good thing. We're going to do FTC part 2. FTC part 2. So step 1, take out the t, so there's where the variable of t used to be. Now notice what I'm doing with the cube on the cosine. I'm putting it on the outside. I took out the t. Now I'm going to put in the new function, which is up here, the variable of x. So take out the t, put in the new function, and then lastly, by the chain rule, we're going to multiply by the derivative of the new function. Now remember, folks, the new function is just x. It's not cosine cubed, none of that mess. So f prime of x is cosine of x quantity cubed. I need the derivative at pi, so f prime of pi would be cosine of pi, I don't know why I have so many parentheses here, cubed. The cosine of pi, remember your unit circle is over here. It's the x coordinate, -1. So that's -1 cubed, which is -1. So now I have the slope. Slope is -1. All right, writing the equation of my line. Remember, I have to get y by itself, and it looks like I might have to distribute in this case to find my multiple choice answer. So y1 is 0. That's nice. Slope is -1. X minus pi, distribute, and that gives me -x plus pi, y equal. -x plus pi is right here, letter E. In problem number 6, we see that we have a calculator permitted problem. We're looking for the area. Now, students, when the problem says the area of the region, it's not going to be a big deal here because the area is going to be positive, but when it wants the area, it wants the total area. But again, it won't be a big deal here because I've already created the graph, but I want to show you something because a lot of students each year tend to have problems with this because they don't know where to accumulate. I want to see what this calculator does before I tell you what I think is going to happen. So I'm going to get rid of the functions that I have in there, and I'm going to have y equal to square root of 1 minus x raised, whoops, no, wrong thing, sorry. Come on, you can do it, I believe in you. X raised to the 4th power, and I'm going to do a standard viewing window of zoom number 6. So there's my zoom number 6. All right, now that graph is very, very teeny tiny. And so if you look, I don't know, I'm just playing around. If you look at the table of values, so second table, I'm just wondering. So when x is equal to 1, we get 0, and I'm going to go backwards. And when x is equal to -1, we get 0. That was really kind of important because, oops, we'll come back, calculator. So when I look at the graph, it's really hard. It doesn't really necessarily look like the graph touches the x-axis at 0 and 0. And so that's what I was showing right here. When you graph this on your calculator, even if you make it bigger than what mine was, sometimes it doesn't look like the graph is touching 0 at those values. So really all this is, when you look, you have to look at that graph on your calculator to know that you're accumulating the area beginning at -1, stopping at 1, under 1 minus x to the 4th dx. So I'll go back to my calculator, and I'm going to go, I made this a little bit smaller. I can't really, I'm not real happy with it because it covers my flip chart, but now it seems like it's too small maybe for you guys to see. Anyway, so I'm going to go to the home screen, second quit. I'm going to integrate math number 9, and I'm going to start at -1, stop at 1, and the function for this problem is in y number 1, so I'm going to use my shortcuts. Not everybody has shortcuts. I'll tell you what to do if you don't. I'll try to keep reminding you how to use your calculator. dx, enter, and I get 1.748. 1.748 is letter E. Now, if you don't have the shortcuts to get to the y1, you, on your screen, or on your calculator, I'm sorry, you hit the vars button, and then you go to Y vars. You'll see that to the right, and then you're going to select function, which is the first thing you see. And when you do that, you'll be able to select Y1, Y2, or whatever it is you want to use. Problem number 7. In 7, they give us a second derivative to be 6x plus 12, which is linear. They want us to find f of x. They want us to go back to the original function. So that is our ultimate goal. So we know we're going to do some anti-differentiation to go from the second derivative to the first derivative to the original function. If the graph of the original function, notice how I'm reading, is tangent to the line 4x minus y equal to 5. Now that's really significant, because the definition of derivative is slope, capitals, of tan line. So this is a really sneaky way of giving us a point on the first derivative. So if I get y by itself for this linear equation, hopefully I'll be careful with so I'll subtract 4x and then divide by -1, and that'll give me 4x minus 5. So the important thing here is the slope, or the derivative, f prime of some number is 4. Well, here's the point back here. They're saying the tangent line is tangent to our curve that we have not found yet at x equal to 0. Therefore, f prime of 0, the slope of the tangent line, which was right here, is equal to 4. So that is a point on f prime. Then lastly, they tell us, okay, well, on the original function, because we're going to need that to find the value of c, f of 0 is equal to 5. So here we go. We're going to find the antiderivative of the second derivative, 6x plus 12, and that's going to take us back to the first derivative. So give me 6x squared over 2, which is 3x squared, plus 12x plus c. And I'm going to set, remember this is the first derivative, so I'm going to substitute 0 in place of x and a 0 in place of x. That'll give me c equal to 4. It's always nice when they give us a 0 value. Do not assume that c is always the number that they give you. It just works out this way because they give us an x value of 0. So f prime of x, maybe should go purple, f prime of x, first derivative function, is 3x squared plus 2x plus 4. Now we're going to go blue. We're going to find the antiderivative of f prime. So that gives me 3x. So the antiderivative of 3x squared plus 2x plus 4 dx is x cubed plus x squared. I'm using the reverse power rule, plus 4x plus c. I'm going to substitute a 0 in place of x, a 0 in place of x, a 0 in place of x. I'm using the initial condition of 0, 5, so that means that c is equal to 5. So the function that we were looking for, f of x original, is x cubed plus x squared plus 4x plus 5. So the main thing with these problems is the way that they ask them, and you have to really think about them. I just noticed that that's a -5, so let's go ahead and fix that. That's a -5. Glad I caught that. So, let's see. Did I notice? Oh, I noticed one other mistake. I bet you guys caught it while I was doing it. That's a 12. So that's going to be a 12. So that's going to be, when I anti-differentiate, that's going to make that a 6. Let's go blue, 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 blue. Go Duke. 6. I'm glad I paid attention to all these things. I hope you caught them as I was going along, and now you know that I caught them myself. So it's a good thing I caught my mistake in letter A because I'm finding the average value of the f of x that I found in A. So average value says to use the calculus formula on f of x. So we have 1 over b minus a. 1 minus negative 1 is 2. Accumulate area from -1 to net area from -1 to 1. And our function is x cubed plus 6x squared plus 4x minus 5 dx. Keep the 1/2. Find the antiderivative, x to the 4th over 4 plus 6x cubed over 3 will give me 2x cubed. And then 4x squared over 2 gives me 2x squared minus 5x evaluated from -1 to 1. So that's going to be 1/2 of, I'm substituting positive 1 in place of x here, 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 and here. So so that would be 1/4 plus 2 plus 2 minus 5. So that is the substitution of the upper bound minus substitution of the lower bound. So I'm going to substitute -1 into the same places. -1 raised to the 4th power is +1, so 1/4. -1 to the 3rd power is -1, that's -2. -1 squared will be +1, so that's 2 plus 5. Now instead of cleaning on the inside of each of them, I try to look for ways to make my life easier. Hopefully it's going to be easier. There is subtraction right here, which has to go, whenever I do the arithmetic, I have to make sure that it goes to all the numbers. So when I take +1/4 minus 1/4, my fraction issues are gone. So now at this point, I think I will clean on the inside. 2 plus 2 is 4. 4 minus 5 is -1 on the inside. I still have a half on the outside. -2, so that's going to be minus. -2 plus 2 makes 0, and so that's going to be a -5. 1/2 of, -1 minus 5 is -6, and half of -6 is -3. All right, and problem number 8. I love this problem because it is truly a thinking and spending way more time at the beginning of the problem up here at the top and not reading any of the letters down here. Now we have a function that they talk about a function f and they talk about a function h. So we're going to have to figure out that relationship. So one thing that I know to be true is that f is negative for all values of x. I know that f of 1 is 0. Which of the following statements must be true? Well, let's play and work around with this first of all. So I'm going to think of h of x as my original function. Let's think about h prime of x. So h prime of x would mean that we are going to take the derivative of this definite integral right here. So we would take out the t. So f of blank, we would put in the new function, which is right here, of x, and we would multiply by the derivative of the new function, which is 1. So it's really important to know that h prime of x is equal to f of x. And I'm going to go ahead and find, so the second derivative of h is equal to the first derivative of x. Now back here, that's kind of important because they told us that f has a negative derivative. That means that f prime of x is negative all the time. Let's see, what else do we have? We have our fact up here that f of 1 is 0. So let's see how all of these facts, I'm going to erase this right here in just a sec. No, that's not what I tried to do. I'm going to erase this right here. We have our facts up here at the top, and we're going to have to come back up here to answer our questions. So, the first question is, does H, and I meant to go with blue, have a first and second derivative? Well, we come over here and we know that H prime of x is equal to f of x. So yes, H prime has a first, or H has a first derivative. And the second derivative of H is the first derivative of x. And it says, or the problem says, f is negative all the time, meaning that there is always a y value. So I have to use this whole connection between h and f to figure out these questions about h. So yes, h is twice differentiable. Letter B. H, look at this, h and h prime are both continuous. Well, based on the first question, since we know that there is a first and a second derivative, if the second derivative existing tells us that h prime is continuous, and h prime existing tells us that h is continuous, so that is a true. Are they asking true or false? Yeah, this is a true. And this is a true. Has to be. Letter C. The graph of h has a horizontal tangent at x equal to 1. Or they could say, and this is how we have to think about it, h prime of 1, is that equal to 0? Well, h prime of 1, look right back up here, h prime of 1 is equal to f of 1, and look at the fact at the top, f of 1 is 0. That is a true statement. So you have to go slow. You have to use your box of knowledge, or boxes of knowledge. Here's one box of knowledge. Here's another box of knowledge, and then we got this box of knowledge out of the interpretation. Letter D. H original has a local maximum at x equal to 1. Well, we just said in the last problem that h prime of 1 equal 0. So 1 is a critical number for h. We cannot tell whether the first derivative changes from positive to negative. Well, in fact, we cannot tell if the first derivative changes from positive to negative, but we do have the second derivative. The second derivative, h prime of 1. So look back up here what we said. Second derivative of h is first derivative of f, and f prime is negative all the time. So if we have a critical number of 1, and we substitute that critical number into the second derivative, and we get a negative, which is what we're getting here, then we have a local maximum by the second derivative test. So that is a true. If there is a local maximum at x equal to 1, then h cannot have a local minimum at x equal to 1. So that's easy. That's a false. The graph of h has an inflection point at x equal to 1. Well, we already know that there is a local maximum on the original function at x equal to 1. So that's not going to be, if you're a local maximum, you're not going to be a point of inflection. Concavity does not change there. So that would be a false. And finally, this says dh dx. I'm not going to read it like that. H prime of x, which is the same thing as f of x, crosses the x-axis or has an x-intercept at x equal to 1. Well, they tell us at the top f of 1 is 0, which means that h prime of 1 is equal to 0. So let's see, do we know that there's a cross, though, or is it just a touch? Let me think about that. So if you think about it, we know that h prime hits the x-axis at x equal to 0. Let's come back up here to our box of knowledge to see what we know. The second derivative right here, the second derivative of h is negative all the time, which means that h prime decreases. H prime decreases. So if h prime is decreasing, remember h prime is f, if h prime or f is decreasing, then yes, there has to be an x-intercept because we're hitting 1, 0. So before that, the y values had to be positive, and after that, they had to be negative. So that last statement would be a true. Those are really good thinking questions. Okay, let's see what we have next. In number 9, we're finding in all of these items the derivative of definite integrals. So let's just take a quick look. In number 9a, I see that my constant is in the lower bound, which is where I want it. In letter B, I see that the constant is not in the lower bound, so I'm going to go ahead even before I do the problem and do a rewriting negate. When we reverse the bounds, we reverse the sign. 7 to x of the square root of 2m to the 4th. So the only thing I'm changing here is I'm reversing my bounds to fit the format of the FTC Part 2. By the way, we're finding the derivative of a definite integral, FTC Part 2. In letter C, I have the same situation. My bounds are out of order. You are out of order, sir. So we have, I'm going to reverse, negate, x cubed. I'm not going to write the function. I'm just going to remind you of that. And in letter D, we have our variable to variable situation. So here we go, FTC Part 2. So to find the derivative of a definite integral, I keep the integrand. So I take out the t. So that t is out. I'm going to do it in the denominator. Take out the t. I'm putting in the new function, and in this case, the new function is the variable x. So I put in an x, and I put in an x. Now, when you multiply by the derivative of the new function, folks, you don't do it for each variable of x. You do it one time. So the new function is x. The derivative of x is 1. So I don't do it in the numerator and then do it again in the denominator. So actually, my answer just turns out to be that right there. In letter B, that's pretty easy. I'm going to negate, keep that negative. So I'm going to take out, in this case, the dummy variable is m. So I take out the m. I take out the m. Keep the 1. And I put in the new function. So the new function is x. So I put in an x, and I put in an x, and I multiply the whole thing by the derivative of the new function, and the new function is 1. So I just multiply it once on the outside. Letter C, the bounds, we reversed them right here. Let's bring this down. So remember, we're going to take out the t and take out the t. We're going to put in the new function of x cubed. So there's x cubed and x cubed. And then here it is, chain rule, multiply by the derivative of the new function one time, not in the numerator and the denominator, the whole thing. So this 3x squared can stay in the numerator. So I have 3x squared cosine of x cubed. In the denominator, when I simplify power to power, I get x to the 6 plus 1. In letter D, we have a variable lower bound of the square root of x and a variable upper bound, square root of x. So we do the process twice. So in other words, we're going to start with the upper bound. So I'll write it here in purple. And then remember, we use the operation of subtraction by the FTC Part 1, and I'm going to do it for the lower bound. So for the upper bound, I take out the u, so I have square root of blank. I'll put parentheses there. And for the lower bound, I'm also going to have square root of blank. All right, let's take out the t. Now I'm going to put in the upper bound new function. So that's going to be an x cubed. Now in this case, I have to multiply by two different derivative of the new function. The derivative of x cubed is 3x squared. I just wrote it in front instead of in the back. And then when I substitute here, I get square root of x. And when I take the derivative of the square root, remember, square root of x is x to the 1/2. That's going to give me times 1/2 x to the negative 1/2. Now, as far as cleaning that up, I guess you could say that that's 3x squared times x to the 3/2, and then minus square root of x is x to the 1/4 power, because it over here is x to the 1/2 to the 1/2. So that's x to the 1/2 power times 1/2 x to the negative 1/2. Okay, cleaning that up, first term I can get 3x, keep the base and add the exponent, so 4/2 plus 3/2 makes 7/2. That's first term. Second term, I'm going to bring that 1/2 coefficient in the front. That's x to the 4th times x to the negative 2/4, so that would be x to the negative 1/4. So you just have to do a little bit of fraction work there. Oh no, I left off the sign U, poopy dogs. I am noticing that now. Thank you for letting me know. So let's see if we can get it in here. Sine of x cubed. All right, so I'm sure you caught it, but yay, so did I before I got way too far behind. So in here, I'll have a sine of square root of x. That's going to transfer. This has to go here, so I have sine of x cubed multiplied. And in the back, I will have sine of square root of x. So let's do a rewrite on the final answer. That'll be 3x to the 7 halves sine of x cubed minus 1/2 x to the negative 1/4 sine of square root of x. And just FYI, when even though we are substituting the x cubed into two places, here and here, we only multiplied by the derivative of the new function one time. Same thing on the other side, even though we're substituting the square root of x and the square root of x twice, we only multiply by the derivative one time. All right, in number 10, we have big F is a definite integral. Little f is a definite integral. And we are finding big F prime, second derivative of big F of 2. So I'm going to come over here for this F prime, the first derivative of big F is equal to, this is FTC part 2 again, I'm taking the derivative of a definite integral, take out the t, so F of blank, put in the new function, which is here, x, and then the derivative of x is 1. So F prime of, the first derivative of big F is little f. Little f is right here. So now I'm going to get to the second derivative of big F. I have to take the derivative, first derivative of little f. So I'm going to do FTC part 2 again. So I will take out the t, so 1 plus, or take out the u. See, that's why I told you it's a dummy variable. Take out the u this time. Take out the u, and take out the u. The new function is t squared here. So I'm substituting a t squared in the numerator and a t squared in the denominator everywhere that there was a u. And I'm only going to multiply by the derivative of the new function one time, the 2t. I'm supposed to be finding that at a specific value 2. So I'm not going to say equal to because now I'm substituting. But that would give me, maybe I should clean that up. So this would give me 2t square root of 1 plus t to the 8th. Remember, power to power, you multiply the powers, over t squared. If I substitute 2, that'll give me 2 times 2 times the square root of 1 plus 2 to the 8th power over 2 squared is 4. So right in front of the radical, 2 times 2 is 4, divides out with a 4. And that's not 1 plus 28, that's 2 to the 8th. So 2 to the 8th power is equal to, let's see, 2 to the 5th, 32, 64, 256. Yes, 256. 2 to the 8th is 256 plus 1 is 257. So the second derivative of big F at 2 is square root 257. Problem number 11. This is a calculator permitted item. They're giving me a differential equation. They're giving me a derivative. And this is y for the original function and x. So this is a given condition of original function. So when x is equal to 5, so it's like they're giving me the 0.54 on the original function, meaning 4 units of area have already been accumulated, and we start at the x value of 5 to accumulate more area. So this is an initial condition problem. So again, in letter A, and I'm not going to evaluate all these out. You can use your calculator to do this. I've already shown you how to use your calculator. 4 units of area already accumulated. Start accumulating more area at 5. And for letter A, we want to stop at 7. And we're going to accumulate area with our calculator under, notice what I'm doing, I'm writing it the way that I want to type that into my calculator. So when I type this into my calculator, I'm going to type exactly what you see, and you can do that calculator work, and the answers are provided in your packet. I'm just going to do your setups. Letter B, 4 units of area accumulated. Start the new accumulation at 5. Now look at this one very carefully. And we're going to accumulate to 0 under sine of x cubed. Look at the bounds. Look at the bounds. They're out of order. So we're going to use our integral properties to change that into 4. You don't have to, guys. You don't have to change it. You'll get, if you type this into your calculator, this right here, into your calculator, you will get the right answer. If you want your bounds in order, then if you reverse the bounds, you have to reverse the sign. And if you don't believe me that you'll get the same answer, type both of these exactly as you see them in your calculator, and you'll see, okay, I do get the same answer. Letter C, the area accumulation again starts at, or there were 4 units of area accumulated. We're going to start the new accumulation at 5. We're going to go backwards to -2. Same function, sine of x quantity cubed dx, and whether or not you want to change the bounds, it's the same thing as 4 minus -2 to 5, sine of x cubed, and you're going to get your answers off of your calculator and confirm it with your posted answers or your answers in your packet. All right, let's see what number 12 holds. We are evaluating without a calculator, and then we're going to check our answer. That's really just an opportunity for you to practice using your calculator. The answers are in your packet. I don't know that I will necessarily work all the arithmetic out, but mostly just set them up. Letter A we're not doing. In letter B, I'm going to begin by doing a rewrite to make that x to the -2 power. And when I increase the power by 1, be careful, that goes to -1. Divide by -1. Check your bounds to make sure they're in the right order, and they are. I'm going to rewrite that to be -1 over x from -2 to -1. I'm going to substitute the upper bound. So if I substitute, that'll be -1 over -1. Remember, we subtract. Be really careful here. There's lots of subtraction. So upper bound minus lower bound. This minus right here is the subtraction of FTC part 1. It's not the negative right here. I still have to have a -1 over -2. So that's lots of craziness going on right there. So for the first term, -1 over -1 is +1. I have 1, 2, 3 negatives, so that'll be -1/2. And 1 -1/2 is, come on, you can do it, is 1/2. For letter C, the antiderivative of x squared is x cubed over 3. I would make square root of x into x to the 1/2. The antiderivative, I'm going to increase the power by 1. That'll take me x to the 3/2. Divide by 3/2 is multiply by 2/3. I check the bounds to make sure they are in order, and they are in the proper order. I'm going to substitute, and I'll get 1/3 plus 2/3 minus 0. Gotta love 0. And that's 3/3, which is 1. Letter D, I have to think trig. So clear annotations, please. Letter D. The antiderivative of cosecant squared theta, first of all, it has to be, we have to get that negative back, so that's going to be negative. Cotangent theta, make sure you use the right variable, from pi over 6 to 5 pi over 6. That's going to be negative. I'm going to go ahead and change. So the easiest way, if this was on an assessment and no calculator, that would be negative cosine of 5 pi over 6 over sine of pi over 6, upper minus lower, minus negative cosine 5 pi over 6 sine 5 pi over 6. So the minus is the FTC part 1, the cotangent's negative, and then we do zip zap. So good news, we get 0. We don't have to do the trig work after all. You are very, very lucky. All right, so I just see that I had totally had a brain freeze on that last problem. I don't know what in the world I was doing. So let's go back to that and let's pretend that I never said any of this part right here. Why I was not even going to get into it. Okay, so let's try that again. Upper bound minus lower bound. So that would be minus cosine of 5 pi over 6 over sine of 5 pi over 6. So that would be substituting in the upper bound. So there's the negative cotangent. And then minus from FTC part 1, the opposite of cosine of pi over 6. So we're not going to get 0 because we're using two different angles here. Cosine of pi over 6. All right, so let's think back to our unit circle. Pi over 6 is 30 degrees, and 5 pi over 6 is going to be in the second quadrant over here. So the cosine of 30 degrees is root 3 over 2, and the sine is 1/2. Over here we have negative root 3 over 2 and positive 1/2. So cosine is negative root 3 over 2, so that makes positive root 3 over 2 over 1/2. Minus minus makes a plus. The cosine of pi over 6 is root 3 over 2. And this, good gracious, what is wrong with me? And the sine of pi over 6 is 1/2. I think I need to go to bed. So that's going to give me 2 times root 3 over 2, which divides out. So that's going to be root 3 plus root 3, which is 2 root 3. Yes! Okay, you don't know this, but it's late when I'm making this video, and I think it's time to go to bed. But I'm going to push through and finish up. Number 13, find the area, that means total area, of the region bounded by the x-axis and the curve y equal x cubed minus 4x on negative 2 to 2. So this would be a calculator problem. because I'm not expecting you to graph and figure that out on your own. All right, so x cubed, let's see how I can get this on here, and x cubed minus 4x, x cubed, area out of there, minus 4x, make sure that's right. Okay, and I'm going to do a zoom 6 window. We're going from -2 to 2. They look like zeros, but I'm going to verify that. So I'm going to put in y equal to 0 for the second graph. In other words, I'm officially graphing the x-axis. I'm going to do a second calc number 5 just to see that we have an intersection. Enter, enter, enter. Looks like we have an even function here. Yep. And so the area from -2 to 0, and what I said, so pay attention, even though there's positive area and negative area, this problem is not asking for the net area. So make that distinction in the words. When a problem says find the area, that means get the total. And so since we saw our graph was an odd function that had positive area and then negative area, we're not getting 0. What we're going to do is we're going to double. I think the easiest thing to do is to double the area accumulated from -2 to 0 under x cubed minus 4x dx. And if you evaluate that out carefully, you will get 8. Number 14 looks like we have an initial condition, so we have the point 112. In other words, this is where we're going to start if we have to integrate, and this is the area accumulated. F prime of x is continuous, and mine is, what is that supposed to say? Let me look in the packet and see if I can see those numbers. So the numbers were from 1 to 4, so we have 12 units of area accumulated. We're going to start at the x value of 1. We're going to stop at the x value of 4. F prime of x is equal to 17, and we're trying to find f of 4. So that would give me 12. If I were to find the antiderivative of f prime, that would take me back to f of x from 1 to 4, that's equal to 17. I'm going to subtract 12 from both sides. So I'm going to do FTC part 1 here, and I'm going to subtract 12 from both sides. That'll give me f of 4 minus f of 1 is equal to 5. F of 1 is equal to 12. So f of 4, all right, let's go back at that again. I wasn't paying close attention. Whenever they're telling me that the accumulated area from 1 to 4 is 17, the 12 is already in there, so I don't need to add that 12 back in. So let me do a restart on this problem. I'll just clear the screen. All right, so we said that this was from the net accumulated area from 1 to 4 of f prime of x is 17. The 12 has already been added in when the anti-differentiation was done. So when we do the FTC part 1 and we find the antiderivative of f prime, that gives us f of x evaluated from 1 to 4 is 17. So that's f of 4 minus f of 1 is equal to 17. So f of 4, we know that f of 1 is 12. So if we add the 12 back to the other side, f of 4 is equal to 29. All right, number 15, let me make a little bit more paper here. Find the average value of the following functions. You can use your calculator to verify, or you can check it with your answers. I'm going to set these up. I'm not going to work these out because this is a pretty long video. So letter A is 1 over b minus a, so that's 1 over pi over 2, which is the same thing as 2 over pi. So 2 over pi, that's 1 over b minus a, from 0 to pi over 2 of cosine of x dx. Carefully do your antidifferentiation. The antiderivative of cosine is sine, and then be careful with your FTC part 1. In letter B, we are finding the average value, 1 over b minus a, so 1 over 3 from 1 to 4 of 1 over x dx. Be careful here, the antiderivative of 1 over x is ln, absolute value of x from 1 to 4. That's 1/3 ln of 4 minus ln of 1. The ln of 1 is 0, and so we have 1/3 ln of 4. We could use log properties. I don't know how the answer is on the paper, and we could put that, make that ln of the cube root of 4. That's just another way we could write the final answer. And then for the last one, 1 over b pi over 4 minus a is the same thing as 4 over pi. So we have 4 over pi from 0 to pi over 4 secant x tangent x. The antiderivative of secant x tangent x is secant x, 4 over pi, evaluated from 0 to pi over 4. And then you can do that and check your answer on in your packet. Number 16, we have 3 more to go. In number 16, big F is the antiderivative of 2 to the x of little f. We're going to use geometry to help us figure things out. So the first thing they want us to figure out is f of 0. So that would be f of 0 is the area accumulated from 2 to 0 of, and notice the bounds are out of order, dt. So if I go from 2 to 0, this area is positive, but I'm going to negate it. I see a trapezoid, so that area would be negative 1/2 base 1, or the height is 2, base 1 is 1, base 2 is 3. Hopefully I did that arithmetic correctly. So 3 plus 1 is 4 times 2. 3 plus 1 is 4 times 2 is 8, or these two knock each other out, so I end up with negative 4. F of 2, that one's easy. If I accumulate area from 2 to 2, I get 0. Area from 2 to 5 is letter C, 2 to 5 of f of x. We're moving in the proper order, so there's 2, 4, 5. We have maybe, let's see, what shape do I want to do here? Maybe looks like a rectangle and a triangle. So that is 1 by 3. So I have 3 units of area there, all positive. And then I have a base of 2. Half of 2 is 1. 1 times 3 is 3. So 3 plus 3 is 6. Net area accumulation. Oh, sorry for the pause. F of 5, we just did that one. F of 7, let me clear the screen here. So we just did F of 5. What did we get for that? So we know that F of 5 is 6. F of 7 is the net accumulation of area from 2 to 7 under F of t dt. So 2 to 5, all this from here to here was already 6. And now we're going to 6, 7 is here. So that is 2 by 1, 2, 3. So f of 7 is 6 minus 3 is 3. So f of 7, 3, minus f of 5, 6 is negative 3. All right, clear? F of 9, we just, we were at f of 7 was negative 3. No, that was not f of 7. F of 7 was 3. Is that right? Yeah. F of 7 we just calculated to be 3. And so now we're going from 7 to 9, which is a trapezoid. So that's going to be let's just go straight across. So we had 2 to 5 was 6. Well, this is negative 6, so we have 6 minus 3, and the area, this is a trapezoid, so the base is 2, so plus 1/2, the base is 2, the height is 2, base 1 is 1, 2, 3, base 2 is 2, so that's 5. 2's divide out, so 6 minus 3 is 3, plus 5 is, I think I calculated that wrong. I see what I did. The area from 7 to 9 is negative, so that's 3 minus 5, which is negative 2. Yay. Letter F. Where does F original have a maximum value? So if we do FTC part 2 on the statement up here, f prime of big F prime of x is equal to f of x. So the first derivative, this is f prime of x. So f has a maximum value. Let's see, are they looking for local or absolute? So I don't think that question is clear whether they want absolute or relative. So I'm actually going to tell you guys not to do letter F. I'm going to throw that out, so I need to make myself a note. And then the average value, letter G, of 2 to 9. Remember, we just found f of 9, which is was the integral from 2 to 9, and we got negative 2. So now if we divide by 1 over b minus a, 9 minus 2 is 7, so we get negative 2/7. In number 17, G is a definite integral, and we want to know local maxes and mins of G. So we need to know when G prime changes from either positive to negative or negative to positive. So by FTC part 2, G prime of x is, take out the t, put in the new function, multiply by the derivative of the new function. So this is G prime of x. We can see that G prime of x changes from positive to negative at x equal to negative 1. So x at x equal to 1, there is a local max, or G, I should say, has a local max. We can see that G prime changes from negative to positive at x equal to 3. So at x equal to 3, G has a local min, and at x equal to 5 is positive to negative, so that would be back to a local max. At x equal to 7 is change from negative to positive, so that would be back to a local minimum. And I told you not to do letter B because this problem is not set up for you to do that well. In letter C, on what approximate interval is G concave downward? We have a graph of G prime, and according to the All About Me sheet, where G prime decreases, let me erase here, where G prime decreases, G original is concave down. So G prime decreases from 1, it looks like a half, decreases from half to 2, from 4 to 6, and from 8, I guess, to infinity. concave down? And the answers are written on your paper, so I'm not going to write them up. I also told you not to worry about sketching the graph of G. All right, number 18, last problem. Long video. I think this might be the longest video ever made. If a cup of coffee has a temperature of 95 degrees in a room where the temperature is 20 degrees Celsius, so the coffee's hot, the room is 20 degrees Celsius. According to Newton's law of cooling, the temperature of the coffee after t minutes is given by this function that you see here. What is the average? And right here, where you see average, students, understand, when it says average temperature, you can insert value of. That's the easiest way to figure out what you're to do. If it just says average temperature or average velocity or average, I don't know, whatever, you can insert value of, and that helps you to know you're doing an average value problem on the temperature function. So with your calculator, you're going, what is the average temperature during the first half hour? And t is in minutes, so be careful. So you're going to 1 over b minus a, 30 minus 0, from time 0 to 30 minutes of, and you'll actually have the function into your calculator, dt. And when you calculate that out on your calculator, you will get a temperature of 76.399 if you round degrees Celsius. You could truncate that to 398. Okay, so this was a long video, but you're probably just using the problems or the parts of the video that you need for your problems, and I hope this helps you for your test.